Okay, now that we've talked about conduction to death, let's talk a little bit about convection. It turns out that convection is actually, pretty simple. It's just natural buoyancy of things. We know that hot air tends to rise, it tends to be less dense. So think about having a wood stove right here, and you have some conduction going on. You have, some air touching that metal, bouncing into it, getting hot, and then the hot air tends to rise, and it tends to take the heat away from the hot stove. And it's going to go up, it's going to cool down, it's going to descend, and just kind of have a nice little cycle just like that. One example of this is going to be the sea breeze, and I'll talk about that in a couple of slides. It turns out that we can actually see convection. One thing to keep in mind though is it's going to apply to any fluid, so any liquid or gas. We're going to have convection where hot air tends to rise, hot water tends to rise. You can kind of see that shimmer on top of the hot blacktop on a really hot day. That's an example of convection. You can kind of see it in a fluid where we have a kind of a hot pipe right there, and the end of this is very, 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 very hot. The water right here is kind of bumping into it, and the hot water tends to rise, and you tend to see this shimmering just like that. That's simply convection, and you can also see this in liquid pots and stuff like that. I have another one of my little fun video demos here where I'm going to take a match and I'm going to put it to an air balloon, and of course that one's going to pop. You go ahead and you do this to a water balloon, a balloon filled with water, and essentially the water is going to convect quite well, so we're going to have some hot water, and it's going to kind of go like this. It's going to take the heat away, and the balloon is not going to pop. Kind of advertise a perfect example of convection is going to be a sea breeze, where essentially if you think of the sun right here and it's kind of beating down on this guy camping right here, and it's also beating down on the water. Turns out that we know that water has a very high specific heat compared to land, so it's going to become hotter over the sand than it is over the water, and hot air tends to rise, so it's going to go in that direction. And kind of what goes up must come down, so you have air going up right here, you're going to have cold air coming down right here, and kind of fill in the circle, and you're going to get a nice sea breeze where it's blowing from the ocean to the land during the day. Interesting thing at night is keep in mind that water has a high specific heat, so it's going to keep its temperature relatively well. It's going to be warmer than what it is right here, and so this whole cycle is going to reverse, where we have hot air right here kind of rising up, cold air coming down, and the sea breeze is going to reverse itself at night. Now, just really quickly, I want to distinguish, an example of forced cooling versus convection. Forced cooling is not going to be convection, and if you think about the wind chill factor, for example, where if you have a person and they're warming up the air that's around them, so you get all this hot air kind of around you. And natural buoyancy says, okay, well, this stuff is going to, the heat's going to rise away from you, and it does, and that is convection. However, if you take a wind and the wind blows on you and it blows all of that hot air away, so blowing it off to the side, not allowing it to rise, that would be forced cooling, and that is not an example of convection. Convection is just natural buoyancy, hot air tending to rise. So any fluid moving across of a surface is going to force some cooling. It's not going to be convection. This is kind of where we get the wind chill factor from, where you say, okay, if it's, 30, 32 degrees outside, but if it's windy out, it feels like it's 16. That's a perfect example of this forced cooling. And this is actually going to be worse in water, because water is a better conductor than air is. Air is a great insulator. And this is, kind of me wearing a wetsuit, where essentially I'm trapping all this hot air next to my body, and it's going to keep me warm in case I go into the drink. So that's kind of an example of a dry suit. A wetsuit does the same thing, except for it keeps a layer of liquid around your body, still trying to keep you warm. Now, the last topic that we need to cover in this chapter is going to be Newton's law of cooling, and really for Newton's law of cooling, I'm not really telling you anything that you don't already know. What Newton's law of cooling says is that the rate of cooling is going to be proportional to the temperature difference, so that's kind of that symbol right there, where that delta is the difference. And just kind of, in short, the rate of cooling is going to be proportional to the difference in temperature. Now, the reason why I told you that I'm not telling you anything that you don't already know, it's because you know that if you have a pie, for example, and it's going to cool off a lot faster if you stick it in the freezer than if you leave it on the kitchen table. The reason for that is because the change in temperature is going to be greater when you stick it in the freezer than it is on the kitchen table, so it's going to cool off faster. And this is kind of why, if you think about it, if your house is really, really, really warm compared to the outside temperature, so if you jack the heat up, then it's going to leak more energy than a house that is kept colder. And that's kind of why you hear those ads in the wintertime where you say, okay, lower your thermostat and you're going to lose less energy. Now, just because it says Newton's law of cooling, don't want you to walk away from this thinking that it doesn't apply to warming as well. Newton's law of cooling is going to apply to warming just as well. And essentially it says an object's going to warm up at a rate proportional to the temperature difference. And again, I'm probably not telling you anything you don't already know. That you know that if you take some frozen food and you stick it in a warm room, then it's going to warm up faster. If you put it in the refrigerator, or if you put it in the freezer, for example, then it's not going to warm up nearly as fast.